So, domains of composite functions, what we got to worry about is, we can certainly do all the algebra. And for this one, as you noticed, that for this one, once you find the domain of f g of x looks like it has a vertical asymptote or x equals 1/3 not included. And that's right for the composite function. But so that by nesting them in, we introduce that other limitation. But the original limitations never go away. They're always there. And sometimes the easier way to understand this, I think, is to treat it separately. What if I wanted to find, so like for this one, first off, x can't be equal to 1, right? So even though with a composite function, I can substitute in 1 and get an answer, if you break it out, if you think about the composite functions, if I'm trying to find f of g of 1, well, that says find g of 1 first. So if I drop 1 into as an input into the g function, I get 2 over 0 out, which doesn't exist. So I can't get an answer because 1's not in that domain. So I've hit a stop sign. I can't continue because I have nothing to substitute into the f function now. So um, what happens when you nest them like this is x equals 1/3 is a domain limitation, so x can't be 1/3, and also that original one from g of x can't be equal to 1, and then I think, well, of course, we're not going to drop anything. So the 1/3 comes from. So then I'm asking myself, what's the limitation here? Um, when is I can have this original function for f, I can't have x be equal to -3. So then if I'm dropping something from this function into here, I can never be equal to 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 3 or -3, right? So where does that happen? Well, you've already done the work here, but I'll show you why. So what I'm looking for is where does g of x, the 2 over x minus 1, equal -3? Because we know if it wherever it's equal to -3, that's not going to be included in the domain. So I'm going to solve this equation. I'm going to treat it like a proportion. I'm just going to write the cross products, cross multiply. I'll distribute that -3 through. Now I'll solve at x. I'm going to subtract 3 and divide by -3. So when x equals 1/3, g of x, so g of 1/3 is actually equal to -3, and that wouldn't work. And you see how we already found that when we did the composite, the nested composite, we knew it could be equal to 1/3. So, yeah, the original domain limitations are there, and it shows up. The one with the 2 over x minus 1, where x can't be equal to -1, didn't show up. And I even played around with graphing in Desmos, thinking it should pick it up, and it didn't. So the calculator didn't catch it either. So okay, so that's one way to talk about domain of composite functions. Break it out separately and see if it works. So then for that other question you wrote, I don't remember what problem it was. It 33 on that section? It said p of x equals 1 over the square root of x, m of x equals x squared minus 4, and we're looking for the domain of m of p of x. So we're nesting p in first. So the first function, if we're thinking about function machines, those in and out machines, p of x will be first, so 1 over the square root of x, and then here's our m function. Whoops, I need my output. That's going to be x squared minus 4. Now, that polynomial has no domain limitations, right? No square roots, I'm not divided by 0. But this other one, x can't be equal to 0, right? Can't find the square root of 0. It can be anything else. Actually, it doesn't have to be x. It has to be greater than or equal to 0, now that I'm thinking about that. Not equal to. Because I can't take the square root of a negative number because it's in the denominator. Okay, so that's the domain limitation from above. So I can't I can't drop in 0. I can't drop in I can't drop in -1 because that would be 1 over the square root of -1. No, I can't take the square root of a negative number. So that domain limitation will be held out. So because this doesn't have any domain limitation, so even though when I drop in 1 over the square root of x squared minus 4, so that's the composite function m of p, that does become 1 over x like you pointed out. And in this case, x just can't be 0 because I can't divide by 0, but I got lost the square root, so it doesn't change it. So, but what we're losing in all this is that we can't take the square root of a negative number, so we lost the greater than 0 thinking. And now if we graph this on, so the domain, to answer the question, the domain of m, this nested function, this composite function, is the same as the domain of p of x in this case. So x has to be greater than 0, or 0 to infinity, and what do we want? We want open on both ends, right? For interval notation, we can say x is greater than 0 in interval or inequality notation. Give me a second, I'll get a graph, and we can see this will show up. So you see how sorry, there's the p of x, there's the m of x, and then I nested p inside of m. And remember how we said x has to be greater than 0 is still the domain, and you can see that now in this graph. I mean, this is not making a mistake. It doesn't get graphed to that x equals 0 is the vertical asymptote, but can't cross that line because I can't take the square root of a negative number. X has to be bigger than 0, so that's what we're seeing in this graph. Okay, so consider the original domain limitations, and then those will follow through in the composite functions. That's the easiest way that I've found to deal with it. Okay, hopefully this helps.